Okay, so we can start. Good morning, everybody. I have received a message from one student about the calculation of the indices of the crystal direction, so I'm going to repeat it quickly. If you want to describe the crystal direction that goes from the midpoint of this side, that is from the coordinates 1/2, 1, 0, to the point 0, 0, 1. This is an example. What you do is you take the first coordinate of the second point, that is 0, and you subtract the first coordinate of the first point, that is 1/2. So you obtain minus 1/2. Then you take the second coordinate of the first point, 0, and subtract the second coordinate of the first point, so you obtain minus 1. And finally, you do 1 minus 0 for the third coordinate, so you obtain 1. So you obtain a triplet of numbers that are minus 1/2, minus 1, and 1. When you consider crystallography, you must avoid non-integer numbers. So you simply multiply by 2 these numbers in order to eliminate the denominator. So minus 1/2 after multiplication by 2 becomes minus 1. Minus 1 becomes minus 2, and 1 becomes 2. So actually what you see is the triplet minus 1, minus 2, and 2. And this describes a crystal direction that is parallel to the original one. But of course, all crystal directions parallel to each other are equivalent. So this is the end of the story. You use this triplet of numbers. Now we go back to the figure describing the sum of the bands of silicon. So we go back to this page. Okay. You remember when we described the relation in the crystal between energy and average momentum, we indicated that the average momentum is proportional to the k vector. So it is customary to use the k vector instead of the average momentum p. And the relation between energy and momentum becomes a relation between energy and k. And in a crystal, this relation has the property of being periodic, so it is sufficient to consider it only within one period, and this period is the Brillouin zone. So the interval on the horizontal axis in this figure is the portion of the Brillouin zone that, for instance, in silicon is between two x points. So the two extrema of the interval of the horizontal axis are two x points. And the k vector, as you can see in the figure, goes along the direction 1, 0, 0 that coincides with the first axis, k1. The other property of the band structure is that there are infinite branches. So you can see only two of them in this figure, but you must imagine that above the upper branch visible in the figure, there are infinite other branches. And below the lower branch, there are other branches, but not infinite. There is a finite number of them. So in principle, if this structure applies to all electrons of the crystal, So each electron has some momentum, that is K, and some energy, that is one of the branches, so it belongs to a point along one of these curves that corresponds to K. Okay? There is still one more property of K. You may remember that at some point we started considering an infinite crystal because actual periodicity is present only if the structure is infinitely extended in all directions. And at some point we said this is of course not true physically. Crystals are finite blocks of matter. So how do we extract a finite block? We simply imagine to start from an infinite block of material and cut this block along parallel planes. Okay, so we extract from the infinite block a finite block. At this point, periodicity is lost because a finite piece of material is not periodic anymore, okay? But if you remember, we invented a trick to restore periodicity. We said we fold, mathematically of course, we fold the crystal onto itself, which means that the left face of the crystal is equivalent to the right face, the bottom face is equivalent to the top face, and the front face is equivalent to the back face. Okay? So we said this trick has a name. It is called periodic boundary condition. We impose boundary condition to the crystal that somehow restore periodicity. Okay? And I anticipated that this trick has a consequence. The consequence comes about after the calculation, so we don't go through the calculation. I simply state the result of the calculation. And the result is that because of the application of the periodic boundary conditions, it happens that vector K is not continuous anymore, but becomes discrete. What does it mean? It means that the three components, K1, K2, and K3 of vector K, that until now we imagine as continuous variables, okay, they are actually countable. They become functions of an integer index, okay? So you must imagine that each component of K is discretized. For instance, this component over the 1, 0, 0 direction is discretized. It depends on an integer index, okay? And this means that the possible values of each component of K are equally spaced along the corresponding axis, okay? So you must imagine that we have many possible values of K on the axis equally spaced, okay? This is not terribly a terrible constraint because we can perform another calculation to calculate how many possible vectors k, after this discretization takes place, are present inside the Brillouin zone. The Brillouin zone is the period in the reciprocal scaled lattice, okay? And it turns out that the total number of distinct or different k vectors in the Brillouin zone equals the total number of cells of the direct lattice. Okay, so the total number of distinct value of vector k is equal to capital NC. You remember the total number of cells of the direct lattice. This number typically is very large. If you take, for instance, a cubic centimeter of silicon, the number of atoms in this cubic centimeter is 5 times 10 to the 22nd. Okay, in silicon there are 5 times 10 to the 22nd atoms per cubic centimeter. So in a cubic centimeter of silicon there is a number of cells that is of the order of 10 to the 22nd. Okay, and this is also the number of k vectors in the Brillouin zone. So it is so enormous that the k vector, yes, it is discrete, but very dense. Its components are very, very dense, which means that if at some point we have a need to calculate a derivative of energy with respect to k, we can do it, okay? We can do it as if the k vector was continuous, okay? Then we have to make other observations, because we said before, for a given k vector, the electron, or the electron that we are considering, has an energy that belongs to one of the branches of the energy, okay? So in principle, we should consider all infinite branches and investigating what the electrons are doing in each of these branches, okay? And of course, if we had to do this, this would be a very, very complicated task, okay? But the issue is that we are interested in the behavior of the electrons, essentially because we want to describe the transport properties of the material. We want to investigate how the material behaves when, after being put in a non-equilibrium condition, there is some electric current flowing through the material. And this electric current, of course, is carried by the electrons. So in order to investigate the current, we must investigate how the electrons move in the crystal in a non-equilibrium condition, okay? Now, some of the bands of the crystal have no electrons. That means that if you go up in energy higher than the energy that is shown in this figure, you find that there are branches. These branches describe possible energies of the electrons, but in fact, there are no electrons that possess these high energies, okay? The reason is easily understood. If you start from the equilibrium condition, the total energy of the crystal is finite. So it is impossible for the electrons to acquire an energy that is too high, okay? Because the total energy that can be possessed by each electron is finite because the total energy of the crystal is finite, okay? So this situation is true also in a non-equilibrium condition. So we may expect that in a crystal, the bands having higher energies have no electrons in them, okay? So, of course, these bands do not give any contribution to the current of the crystal because they don't have electrons. So there is nothing in the high energy bands that can move around and carry the electric current. So the bands that are high in energy are empty of electrons. And when a band is empty of electrons, it gives no contribution to the current, so there is no reason for us to consider that band. That band can be disposed of because there are no electrons. On the other hand, there are bands with low energy, those that are below the lower band of this figure, okay? Bands that are low in energy are completely filled with electrons. That means that to each k vector of the lower band, there correspond an energy, and there is one electron possessing that energy. Okay. So the bands that are low in energy are completely filled with electrons. Okay. Each state, a vector k is also called a state. Okay. So each state has an electron in it. Okay. There is an electron with that k and with that energy. Now, it is not obvious, but we shall demonstrate this with a calculation in the near future, that when you have a band that is completely filled with electrons, that is, each k and each energy of the band has an electron in it, that band is not able to contribute to the electric current. This looks quite odd. One would expect that if that band has many electrons, it should be able to produce a large current. This is not true. A band that is completely filled is not able to contribute to the current. So we have two classes of bands that are useless for our purposes. Those that are up in energy, that are completely empty and do not contribute to the current, and also those that are low in energy, that are completely filled with electrons, and they also do not contribute to the current. In conclusion, out of the infinite bands in a semiconductor, or more generally in a crystal, the only band or the only bands that are able to contribute to the electric current and therefore are of some interest to us are those that are partially filled, meaning that some of their states have an electron in them and some other states do not, okay? It happens that in semiconductors, there are only two bands that are partially filled. And they are the two, in the case of silicon, are the two bands that are visible in the figure. So out of the infinite bands existing in a semiconductor, that is, out of the possible infinite value of energy that in principle an electron could possess, actually only two of them are of any interest to us, those that are partially filled, okay, that are intermediate in energy between those that are empty and those that are completely filled, okay? These two bands, of course, are special because they contribute to the current of the semiconductor, and because they are special, they take a name. So in particular, the upper band that you see in the figure here is called the conduction band, and the lower band is called the valence band. So this also explains why the minima of the conduction band are called EC. C stands for conduction. And the maximum of the valence band is called EV because it belongs to the valence band. Okay. So now assume that those dots that you can see in the figure represent electrons. Okay. So the meaning is that consider, for instance, this dot that I'm indicating with the mouse. This means that there is an electron whose k vector is this one, is the value along the horizontal axis, and the energy is this one, okay, on the vertical axis. At this, if you take a picture of the crystal, there is one electron that possesses this momentum and energy, okay? It may happen that the electron is subjected to an external perturbation. You remember, at some point, let me change. You remember the figure that is visible here on the left, okay? At some point, consider the classical situation of a free particle. We said if a particle has an energy corresponding to the dot 3 prime, okay, and somebody perturbs the motion of the particle so that its velocity and momentum increase and energy also increase, then it will shift to the position 3 second, okay? So this happens identically also in the description using the branches here. Sorry. Okay, because what is different is simply the form of the relation between energy and momentum, but the physics describing it is the same. So if there is an external perturbation, these black dots move around along the curve where they belong. Okay? We shall come back to this very soon, but now I want to give you a better description of the shape of the bands of the most important semiconductors. So I'm going to take a picture. Let me change the screen. I take a picture. This picture is taken from the reference book that was listed in the list of references. Is the book by Z. Z is spelled S-Z-E, okay? So these three figures show the shape of the bands, actually, of the conduction and valence bands of silicon. Silicon is shown in the middle of the figure. Germanium is shown on the left, and gallium arsenide is shown on the right. Okay. These figures may look odd because they are not symmetric. Okay. You expect, as if you remember the other figure that I was showing before, the bands are symmetric from right to left. Actually, if you look at the horizontal axis, okay, you see that if you take the gamma point of silicon and you go to the right, you go along the 1, 0, 0 direction. So you are going from the gamma point to the X point. So the right half of the figure of silicon reproduces the figure that was shown before, okay? You remember there was the conduction band with the maximum here, and then it went down, there was a minimum. This minimum corresponds to EC, and then it goes up again, okay? The left part of the horizontal axis actually goes along the 1, 1, 1 direction. So it goes from the gamma point to the L point. So this is not simply one figure, it's two half figures put together to have a more compact description of the bands. Okay. So you remember that along the 100 direction there are two minima of the conduction band in silicon. If you consider the 010 direction, we have two more minima. And if you consider the 001 direction, we have two more minima. So the conduction band of silicon has a total of 6 absolute minima, and they all have an equal value. It's EC. Okay. In this picture, you see other curves above. They are other branches, other bands, okay, but they are not of no interest because when you go up in energy, there are no electrons, okay. Actually, if you look closely here, you see that near the minimum of the conduction band, you have, these are minus sign, they're minuses, okay? So they simply indicate symbolically the presence of electrons. In the conduction band, some states are occupied by electrons, and the occupied states are those that are near the minimum, okay? So the band is the states of the band, of the conduction band, are occupied near the minima, whereas if you go up in energy, the states are not occupied. So the conduction band is partially occupied, and for this reason, it is able to contribute to conduction. If we now go to examine the valence band, we see actually that the structure of the valence band is a little bit more complicated than in the figure that I showed you earlier, because in the valence band there are two branches. You see there is a lower branch here and an upper branch here, okay? But these two branches have the same value of the maximum. The curvature at the maximum is different, but the value at the maximum is the same. Okay, so there are two branches with the same value of the maximum. You can also see that symbolically there are plus signs indicated near the maximum of the maxima of the valence band. This means symbolically that the electronic states of the valence band are not occupied by electrons near the maxima, okay? So it is dual with respect to the symbol used for the conduction band. When there are electrons, we expect to have a negative particle and put a minus sign symbolically. When an electron is missing, we expect to have a missing positive particle that is, in quotes, like having a positive particle because there is a missing electron, okay? The electrons are missing only near the top, okay? Whereas the states that are lower in energy of the valence band are occupied. So the valence band is, like the conduction band, is partially occupied, and it is able to contribute to the electric current. Okay. Let's now go to germanium. So we go to the left. Again, we have two half figures put together. The right part of it goes from the gamma to the X point, and the left part goes from the gamma to the L point, okay? That is along the 1, 1, 1 direction. You observe that the minimum, the absolute minimum of the conduction band in germanium is along the 1, 1, 1 direction. Actually, it is at the L point, okay? So you remember the total number of L points in a crystal like silicon or germanium is 8. So germanium has 8 minima instead of the 6 like silicon. There are 8 minima in germanium in the conduction band. However, you see this minimum is exactly at the boundary of the Brillouin zone. That means that only 1/2 of the minimum is inside the Brillouin zone and the other minimum is outside. So we must count one half of it, okay? So that means that the total minima of the conduction band in germanium is actually 4, not 8, okay? Because we should count only the part of the minimum that is inside. The valence band has the same structure as in silicon, okay? You see that there is an indication here, light and heavy holes. This is not easily understood for the moment, but we shall come back to it later. It means that the particle that belongs to one of the two branches have an effective mass that is different from the other. We shall discuss this in another occasion. Okay. Let's now go to gallium arsenide. Okay. Gallium arsenide has a valence band whose structure is the same as for silicon and germanium. There are two maxima with the same, two branches with the same value of the maximum. Instead, there is only one minimum in the conduction band, and this minimum corresponds to the gamma point. Okay. Let's consider now the gap. You remember, for each semiconductor, the gap is the difference in energy from the minimum of the conduction band to the maximum of the valence band. So the energy gap is indicated in the three figures for gallium arsenide, silicon, and germanium. Okay, you see that silicon has a gap that is intermediate between that of gallium arsenide, that is larger, and that of germanium, that is smaller, okay? So it is customary to consider silicon as the reference material, okay? Because it's so important for the technological application. For this reason, gallium arsenide, whose gap is larger than that of silicon, is commonly referred to as a large gap semiconductor or wide gap semiconductor. And instead, germanium, whose gap is smaller, is referred to as a narrow gap semiconductor. Okay? The extension of the gap has an important effect on the electrical properties of the semiconductor. Then we make another observation. If you consider silicon and germanium, you see that the maxima of the valence band are in the gamma point. So they correspond to k equal to 0. Instead, the minimum or the minima of the conduction band are not in the gamma point. They correspond to a k vector that is different from the gamma point, okay? Semiconductors that have this property are called indirect semiconductors, okay, indirect. In contrast, gallium arsenide has the maxima of the valence band at the gamma point and also the minimum of the conduction band also at the gamma point, okay? So for this reason, it is called direct semiconductor because the position in the k-space of the maximum of the valence band is the same as that of the minimum of the conduction band. Is this of any importance? It is important because direct semiconductors like gallium arsenide have a much larger probability that the interaction of the semiconductor with the electromagnetic radiation is able to induce a transition of an electron from the conduction band to the valence band or vice versa. What does it mean? It means that if we have an electromagnetic radiation coming onto the semiconductor, this radiation provides energy to the semiconductor. So it is possible that one electron belonging to a state of the valence band acquires enough energy from the electromagnetic field to make a transition up into the conduction band. This is called optical transition or optical absorption because the semiconductor absorbs energy from the radiation. The opposite phenomenon is also possible. You may have the situation in which an electron that belongs to the conduction band loses energy and goes from a state of the conduction band into a state of the valence band. And this loss of energy is emitted as electromagnetic radiation, okay? And this is called emission, okay? So these types of interaction with the electromagnetic field are much more probable in a direct semiconductor, and they have instead a very low probability in an indirect semiconductor like silicon or germanium, okay? This is the reason for which lasers made of semiconductors are manufactured using gallium arsenide, because gallium arsenide is a direct semiconductor. So you can easily manufacture a laser, a solid-state laser using gallium arsenide. You cannot do it using silicon or germanium. Okay. Finally, there is another observation that we can make about gallium arsenide. You see that gallium arsenide has an absolute minimum of the conduction band in the gamma point, but then there is another minimum, not an absolute minimum, but another minimum, still in the conduction band, whose value of the minimum is not so much displaced with respect to the absolute minimum. So the difference in energy is written here is 0.36 electron volts. So it is a small energy. Okay. This is also important because when we consider the equilibrium condition of the semiconductor, we see that the majority of the electrons belong to states near the absolute minimum. Okay, so where the minus signs are indicated here. Okay, so at equilibrium, the majority of the electrons stay here. Okay, when we apply a voltage to the semiconductor, the electrons start moving along the crystal, and in doing so, they are subjected to the electric field because we apply the voltage. So they may acquire energy, and some of them may move from the lower minimum to this upper minimum. Okay, the minima of the conduction band are also called valleys, and also the maxima of the valence band are called valleys. So you see in the figure, it is there is indicated here upper valley and lower valley. Okay, so out of equilibrium, some electrons in gallium arsenide may move in energy from the lower valley to the upper valley. Okay, so they become more energetic. Okay, however, you can see that the curvature of the two valleys is very different. Okay, the curvature of the lower valley is much larger. That means that the curvature radius here is much smaller. And instead, in the upper valley, the curvature radius is much larger. Okay, we shall see very soon that in a semiconductor, the inertia of the electrons to the external forces is not related to the actual mass of the semiconductor, but is related to the curvature of the band. This looks very odd, but it is easily demonstrated that it is so. Okay, so the inertia of the electrons sitting in the lower valley is small. That means that the mass by which these electrons react to the external forces is small. Okay, and in this case, when the electrons stay in the upper valley, the mass is larger. Okay, so there is this oddity that the electrons of the upper valley are more energetic, but they are also heavier. Okay, and those that belong to the lower valley are less energetic but lighter. Okay, the consequence of this is that the material may be become unstable. Okay, so those of you who are familiar with the circuit theory know that if in a circuit you consider the voltage current characteristic, and you find that this characteristic has a portion with a negative slope, okay, the circuit is unstable. And if the circuit is unstable, it produces or it may produce oscillations, okay? The same happens in a material like gallium arsenide, okay? There is a negative slope in the current voltage relation of the material. This may produce oscillations, okay? And it is actually exploited to produce oscillations. This result is very important, and actually it was anticipated theoretically before people succeeded in producing oscillations with gallium arsenide. So it is one of the best evidence that the theory of solid state works. Okay. Also consider that we have spent almost half an hour on this figure. Okay, so this figure it looks simple, but it gives a lot of information. Now that we have anticipated that the curvature of the band or of the extremum of the band is related to the effective mass, so to the mass by which the particle reacts to the external forces, now we can explain why the two branches of the valence band are marked with the indication light and heavy holes, because the curvature of the lower branch is larger, so the curvature radius is smaller and the mass will be smaller, as we shall see. And so the particle that belongs, whose energy belongs to this branch, are lighter. Instead, when we consider the other branch, the particles that belong to this branch are heavier. What particles are they? It is called hole. They are called holes because holes are missing electrons. Okay, so this is another oddity of the solid state theory, but we shall explain also this aspect, okay, very soon. So for the moment, we can stop because we have almost reached 10 o'clock. There are still 2 minutes, so if there are questions, you can open the mic and ask questions. Okay, so no question. I see one in the chat. No. Okay, so we stop here and we shall resume at 10:10. Okay. Okay, so we start again now. We start now considering again the figure of the two bands of silicon. And you remember that we anticipated that if the electron belongs, for instance, to this position along the conduction band, and there is an external perturbation that is a weak perturbation, then this dot moves along the branch, indicating that due to the external perturbation, the energy and momentum of the electron are changing. Okay. In crystals, it may happen that electrons from time to time are subjected to perturbation that cannot be considered weak. Okay. The typical example of strong perturbation is a collision. An electron may collide with another electron, for instance, or with an atom of silicon, or maybe with some impurity that is present in the material, or if the electron is moving near the boundary of the material, it may interact with the surface of the material. And these are all strong interactions, okay? So the strong interactions cannot be described in the easy way as we did for the weak interaction, so we did it by perturbation, okay? These are not to be considered perturbation. These are very strong events, so that an electron may change momentum and energy in a very short time, okay? Consider a classical example of a tennis ball that is thrown against a wall, okay? The tennis ball bounces back, so that means that the momentum of the tennis ball reverses, changes completely in a very short time, okay? So when we have collisions, and they happen from time to time in the crystal, we must consider transitions from an initial state, an initial pair K vector and energy, to a final state, okay? And these transitions may be classified. Actually, there are two methods for classifying the transitions. One method is considering the other object with which the electron is colliding. So we may consider different categories depending on the fact that the electron will collide with another electron, a nucleus, an impurity, a photon, if there is an interaction with the electromagnetic field, or an interface, okay? So this is the first method for classifying the transitions. Another method instead for classifying the transitions consists in observing where the initial and final states are, okay? And this is what is made in this figure, okay? So these dotted lines, like this one or this one or this one, etc., describe transition from an initial state to a final state. It does not really matter which state is the initial one and which is the final one, okay? It is important to consider the transition, okay? So transitions of type 1 have the property that the initial and the final state are in the vicinity of the same minimum or the same extremum of the band, okay? You remember that both minima of the conduction band and maxima of the valence band are called valleys, okay? So a transition like the one that is indicated with the number 1 in this figure, in which both the initial and final state, whichever they are, belong to the same valley, they are called, as you can see on the left, intra-valley transitions, okay? Then there are other transitions like that of type 2, in which the initial and the final states belong to different valleys, but they are in the same band, okay? So this type of transition in which the valley is different but the band is the same are called inter-valley transitions, okay? Both transitions of type 1 and 2 are such that the initial and final state are in the same band. Okay, for instance, 1 and 2 are in the conduction band. Okay, so they are collectively called, you can see it in the left part of the figure, intra-band transitions. Okay, why is it important to distinguish between intra-band and non-intra-band transition? Because the characteristic times of the transitions are very, very different, okay? The intra-band transitions are very fast. Other types of transitions are rather slow, okay? Then we go to a transition like number 3, in which the initial and final states belong to two different bands, okay? So they are called, as you can see on the left, interband transitions, okay? They also take different names depending on the fact that the initial state can be in the valence band or in the conduction band. So consider, for instance, a transition of type 3 in which the initial state is in the valence band and the final state is in the conduction band. So initially we have an electron that belongs to the valence band. For some reason, this electron acquires energy because of a collision with something else, okay? And thanks to this energy, the electron is able to move to make a transition to the conduction band. It goes up in energy. It also changes momentum, of course, okay? So the final situation is that after this transition, there will be one electron more in the conduction band and one electron less in the valence band. This is obvious, okay? And the absence of an electron in the valence band is called hole, okay? So there will be one more electron in the conduction band, one more hole in the valence band, okay? So this phenomenon, this type of transition is called generation of an electron hole pair, okay? Because we have at the same time one more electron in the conduction band and one less electron, that is one more hole in the valence band, okay? The inverse transition, that is one electron that is initially in the conduction band, and then it loses energy for some reason, because of some collision, so that it makes a transition to the valence band. In this case, we have one electron less in the conduction band and one more electron in the valence band, so there will be one less hole in the valence band, okay? So this phenomenon is called recombination of an electron-hole pair, okay? So when it goes up, it is generation, and when it goes down, when the electron goes down, it is recombination, okay? More precisely, a transition of the type 3 is called direct transition, because it goes from the one band to the other without any intermediate step, okay? It is also called interband transition, as you can see on the left, okay? In semiconductors, there is another possibility for the interband transition, and this is described by processes number 4 and 5, okay? The structure of the bands made of an alternation of allowed bands and forbidden bands occurs only if the semiconductor is pure. So if we have a perfect semiconductor with full periodicity, okay? In reality, this never happens, okay? All semiconductors, all crystals have some defect in them, some impurity, some extra atom or some missing atom, we shall see. So if there is an impurity or any type of defect in the crystal, it may happen that there are extra energy states whose energy value is inside the gap. Okay, so you see the short line, the short horizontal line here indicates symbolically the presence of an extra energy state whose energy is inside the forbidden gap. Okay, the short horizontal line indicates symbolically that physically that energy state is only in the position of the defect inside the crystal, not everywhere, not in every physical position of the crystal, okay? So if there is this extra energy state, okay, that is also called trap, because it may be able to trap electrons, it may happen that one electron initially belonging to the conduction band makes a transition of the type 4 from the band into the state. Okay, if the state is empty, then there is a probability that this state may be occupied by this electron. Okay, the electron sits in the state for a while, and then it may go back, but it may also make another transition of the type 5, okay, from the trap into the valence band, okay. So the combination of event of type 4 followed by event of type 5 globally is a recombination, because we have one electron that moved from the conduction band to the valence band through this intermediate step, okay? This is called trap-assisted recombination, trap-assisted recombination. The opposite is also possible. You may have an electron that is initially in the valence band, it goes into the trap, and then after a while from the trap it goes into the conduction band, and this is called trap-assisted generation. Okay. In real life, there are always defects in semiconductors, so trap-assisted generations and recombination do happen, and actually they are much more probable than the events of type 3. That is, they are more probable than the direct transitions, and qualitatively this is easily explained. It is easier to find energy in chunks than to find the total energy that is necessary for the transition altogether, okay? Small energies are more easily available in the crystal, okay? So trap-assisted transitions are more probable to the point that when we calculate the interband transition, eventually we always use only trap-assisted transitions. We never consider direct transitions, okay? Now we have to introduce an important concept. Let me okay. So I don't know whether the new page is visible, so I'll do it like this. Okay. We have to introduce the important concept of density of states. Okay. So for this, we take a simple figure that is the figure that you can see on the right. We assume that the band that we are considering is parabolic. It is not so, okay? Bands are not parabolic, okay? And we remember that the K vector is discretized. So there is a finite number of K vectors in each interval, and they are equally spaced, okay? So we now want to make this reasoning, okay? Consider a value of K. And then consider another value of K plus delta K. So you consider an interval along the K axis. So these dots are not electrons, okay, are possible values of K, and those on the vertical axis are possible value of energy, okay? Now, the initial value of the interval K corresponds to some energy that we call E. The final value of the interval K plus delta K corresponds to a final value of energy that we call E plus delta E, okay? So obviously, an interval of K defines an interval of energy. The green dot is any value of K inside the interval, of course, value of K of those that are admissible, so those that are described by integers, okay? The green dot along the vertical axis describes the corresponding value of energy, okay? So now, you remember the values of K along the horizontal axis are equally spaced because they are counted by integers. So they have a constant density, okay? the corresponding points of energy along the vertical axis are not equally spaced because the relation between K and energy is nonlinear. Okay? In this simple example, it is parabolic, but the reasoning can be repeated also for a non-parabolic form of the band. Okay? So we want to understand how the energy points corresponding to the K points, how the energy points are distributed over the vertical axis. Of course, the distribution will not be uniform because the relation between K and energy is non-linear. Okay? So you remember that the K vectors are discrete, but they are very dense. They are very dense. Okay? So this is one of the cases in which we can use derivatives instead of integer variations because of the density of the K vector. So what we do is we take delta K smaller and smaller, okay, in order to make it infinitesimal. And we count the number of the K vectors that are in this interval. Of course, since the number of K vector is, since the K vectors are equally distributed, the total number of K vectors or values that are in the interval, you see equation 42, is equal to a constant density, Q of K, times the length of the interval that we have made infinitesimal. So Q of K is the density of the K vectors or the values of K along the horizontal axis. And this density is a constant. Okay? The total number of values of K is the density times the extent of the interval, Tk. Okay? But you see from the figure, to each K, there corresponds an energy. So the number of values of energy that are in the vertical segment, of course, is equal to the number of values of K that are in the horizontal segment, because we have a one-to-one correspondence. But the values of energy are not equally distributed. So we must introduce a function that we call G depending on energy, such that G of energy times the length of the energy interval is equal to the number of states. And of course, it is also equal to Q of K times dk. Okay, so G of E is a very important function that is called the density of states in energy. Q of K is the density of the K vectors along the K axis, but this is a constant. This is a very easy concept. Okay. Now we have another information. When the relation between energy and momentum is parabolic, okay, if we use P as momentum, we would have energy equal to the potential energy, that in this case is a constant, plus P squared over 2 times the mass, okay? It can be demonstrated that K is related to the average momentum. You remember K is proportional to the average momentum. And the factor of proportionality is the Planck constant divided by 2 pi. Okay, so you see it in the caption of the figure here. Average momentum P multiplied by H. H is the Planck constant. divided by 2 pi gives you k. Okay. The Planck constant divided by 2 pi takes a name. It is called the reduced Planck constant. And it takes a special symbol. It is a H with a bar. Okay, so H bar is the reduced Planck constant. So momentum squared becomes H bar squared K squared. So the relation of this example between energy and K is this one. Okay. Now, the purpose of the calculation is to determine this function g of a. Okay, you extract g of a from equation 42. It becomes q of k times dk over dE. You write it in this form, so you put dE over dk in the denominator. And then, of course, you extract dE over dk from this relation. And what you get is dE over dk is equal to h bar squared divided by the mass times k. Then you extract k from this relation, and you obtain E minus V0 times 2ma. Then you extract the square root and divide by k. Okay? Now we introduce a new symbol, which is easily understood. The total energy minus the potential energy is the kinetic energy. Okay, so instead of calling the kinetic energy with the symbol T, as we did earlier, we call it E sub E. Okay, this is the kinetic energy of the electron. Okay. Of course, the derivative of E with respect to K is equal to the derivative of E sub E with respect to K, because they differ by a constant. Okay, so dE over dk is this expression, the first expression of 44, in which we may replace k with this expression. So eventually, dE sub E over dk is some constant, the square root of 2 times the reduced Planck constant over the square root of the mass times the square root of the kinetic energy. Okay. Then we remember the expression of G sub E. It is Q of K divided by this derivative. We simply replace this derivative and we obtain the density of states. Okay? The density of states is calculated, is expressed by equation 46 for, be careful, for the one-dimensional case. Okay? This expression applies only when the K space is one-dimensional, because in the expression of the total energy we have used only one K. Okay? So it is proportional to the inverse of the square root of the kinetic energy. Okay? When we consider the two-dimensional case, the density of states is calculated in the same way, but it comes out to be different, because in 2 dimensions, the kinetic energy has this expression, the expression that is on the left-hand side of equation 47. Why? Because we have 2 components of K, K1 and K2. Okay? So the kinetic energy is h bar squared, it's momentum squared over 2 times the mass. Okay? The construction, the geometrical construction also changes because you remember in one dimension, if you look at the figure, we take k and then we increase k by a little, okay? And correspondingly, we start from some energy E and we increase it by a little, okay? So we have a segment on the k-axis. When we consider the two-dimensional case, okay, and if you look at equation, the second of equations 47, this is a circle, okay? We have k1 squared plus k2 squared equal to a constant, okay? So this is a circle whose radius is the square root of the right-hand side, okay? So when we extend a circle, we obtain an annular strip, okay? An annulus, okay? And we must calculate the area of the annulus. This is easy, okay? Because the area of the annulus of radius k is pi k squared. If you extend the radius by dk, you have pi k plus dk squared. If you take the difference to first order, it is pi k dk, okay? So this expression here is the area of the annulus that you obtain by extending the energy by a little quantity, okay? At this point, you proceed as before. You remember that K is the square root of the kinetic energy plus some constant. dk is extracted from this expression here. Sorry, this one. You see k equal to the square root. You take the differential and obtain dk. You replace it, okay? And you obtain this relation k dk, that is the variation in the area of the annular strip, equal to this, expressed in terms of energy, okay? What is the number of states in the strip? Okay, of course, the states are equally distributed in the k space. So it is a constant, qk, times the area of the strip, pi k tk. And this number should not change if you express it in terms of energy. So you replace it and you have this number. Conclusion, the density of states in energy is this coefficient, the coefficient that is just before the E. Conclusion, in two dimensions, when the relation between energy and momentum is parabolic, the density of state is constant. Okay, you see it is a different outcome with respect to the one-dimensional case. In three dimensions, the procedure is the same, but you must use a three-dimensional description that is given by equation 51. Okay. Instead of a circle, you have a sphere. And when you increase the radius of the sphere, you obtain a shell between two spheres, okay? And you must calculate the volume of the shell, okay? But the procedure is quite similar, okay? And eventually, you find that for the parabolic relation between energy and K, the density of state in energy is given by equation 54. It is proportional to the square root of energy. This is the important relation to be remembered. In 3 dimensions, the density of states in energy for the parabolic relation between energy and K is proportional to the square root of the kinetic energy. Okay, and then there are the other constants that are the density of states in K, that is pi, QK. Then there is pi divided by the cube of h bar times twice the mass to the 3/2. Okay, so this is the general expression of the density of states in 3 dimensions. Okay, there is still a little complicacy, but I'm going to show it in these slides. These slides gives you in compact form some properties of the band. Some of them are known, okay? If you take any branch of the energy, so the branch is indicated by this index R, okay? So, of course, we already know that we shall consider only the conduction band and the valence band, so the index is not necessary anymore, but for the moment we keep it, okay? The relation between energy and momentum is periodic. So this equation expresses periodicity in the scale reciprocal lattice. And the second relation expresses the fact that energy is even with respect to momentum. Okay, you remember energy is even with respect to momentum. Okay. Also, we did not tell how to calculate the density of vectors k, q, k. Okay, but you remember at some point we indicated that there is a calculation showing that the total number of the k vectors of the Brillouin zone is equal to the total number of cells of the direct lattice. So the total number of cells of the lattice is NC. So NC here is the total number of k vectors in the Brillouin zone. Their density, of course, is the total number divided by the volume of the Brillouin zone. So NC over tau G is the volume of the Brillouin zone. This ratio is the density of the k vectors, and is a constant, of course. On the other hand, the total number of cells of the direct lattice is equal to omega. Omega is the volume of the direct lattice divided by the volume of the elementary cell of the direct lattice, that is tau L. Okay, so NC is equal to omega divided by tau L. On the other hand, you remember we already made this calculation. Tau L times tau G is 2 pi to the 3rd power. So another way of expressing the density of the k vectors, omega, in the density of the k vectors in the reciprocal scale lattice is omega over the cube of 2 pi. Okay. Now we have to introduce a quantum property that probably it is already known to you. It is called the spin of the electron. Electrons have a quantum property that is called spin, such that when an electron has an energy, actually there correspond two possible quantum states to this energy, and the two quantum states differ by the spin. One of them is spin up and the other one is spin down. Okay. So actually, to each K, there correspond two possible states of the electrons. Okay. So we must distinguish between the density of the K vectors and the density of states. The density of states is twice the density of the K vectors. Okay. It follows that the density of states, Q of K, is 2nc over tau g, which is equivalent to omega over 4 times pi cube. Okay. In many situations, we must consider, instead of the density of states in K, we must consider a combined density of states in the R and K space. The R and K space is 6-dimensional, of course. Okay. But this is quite easy because all the considerations that we have done so far refer to a crystal that is uniform in the physical space. So if we want to find a density related to the physical space, we simply divide by the volume. So the combined density of states is called Q without any suffix. And it is calculated by taking Q of K and dividing by omega. So it is simply 1 over 4 times pi cube. Okay, so Q of K is the density of states. Q is the combined density in the RK space. Now we must introduce a simplification in the description of the bands, because it is easily understood that considering the complicated shape of the bands is inconvenient. Okay. So if we want to describe the physical properties of the electrons, for instance, that belong to the conduction band, in principle, we should take the full shape of the conduction band into consideration. The question is, do we really need this? And the answer is no. Why? Because you remember from the other figures that the electrons of the conduction band belong to the states that are near the minima. It is very unlikely that some electrons occupy states that are up in the band, far from the minima. Okay? So if the electrons sit near the minima, and you consider each minimum at the time, okay, then the form of the band that really matters is the form of the band near the minimum. Okay. But if you take a function and you consider only the small portion of the function that is near the minimum, you may think of simplifying the function by taking the Taylor expansion of the function near the minimum. Okay. So what happens if you take the expansion of a function near the minimum, you have, first of all, the constant that is the value in the minimum. For instance, EC in the conduction band, okay? Then you have the terms of first order in the expansion, but they are zero because you are considering the expansion near the minimum. So the first derivatives of the function at the minimum are zero. And then the next term is the quadratic term, okay? And then you stop the expansion. So we simplify the picture by considering in the conduction band only the Taylor expansion of the band near the minima, and we truncate the expansion at the second order, okay? But in so doing, we obtain a quadratic relation between energy and momentum. So we restore the parabolic form of the relation between energy and momentum that applies in free space, okay? So after the complicacy of introducing the band, we in some sense eliminate the bands by considering a parabolic approximation near the minima. This approximation, in fact, is called parabolic band approximation, okay? We do the same for the valence band. In that case, we take the Taylor expansion near the maxima of the valence band, okay? In this calculation, there is a little complicacy. Why? Because look at the formula, okay? This is the general formula for a minimum, okay? You take the branch E of R of K. The minimum here is called E sub A. Then A will become C, the bottom of the conduction band. But for the moment, A is a counter, it counts the minima, okay? So E sub A is the constant that coincides with the value of the band in the minimum, okay? The name of K at the minimum is called K sub A, okay? You remember, apart from gallium arsenide, the minimum is not in the gamma point. So the minimum is not in the zero of K, it in some position of K that we call K of A, okay? And also, K has three components because it is a vector. So I is the index of the components, K1, K2, K3, okay? So in the parabolic band approximation, you don't have the first order term because we are in the minimum, okay? And then we have the second order terms, and they are 1/2 the sum from 1 to 3 of the second derivatives of the energy with respect to K 2 times, okay, calculated at the minimum A times Ki minus Kia squared, okay. Of course, since E sub A is a minimum, this energy is larger than E sub A because we move a little from the minimum, okay? So the second order part is strictly positive when we move from the minimum, okay? Because of this, we can take the difference between E sub R and the minimum, and we call E sub EA. So E is the index that we already encountered in the calculations that we've done a few minutes ago. A is the counter of the minimum, okay? This quantity is non-negative, okay? Now we have reached 11, so the completion of the calculation will be done in the next hour, but I want to point out a problem. The problem is that the three components, the three derivatives here, the second derivatives of energy with respect to K are not necessarily equal to each other in the same minimum, okay? So the curvature in one direction or in the other direction or in the third direction is not necessarily the same. So in general, we must expect that these second derivatives in the same minimum are different, okay? So we stop here for the moment and we shall resume in 10 minutes. Okay, so we start again. You remember we were discussing the second order expansion of a branch around the minimum. We may simplify the notation because if you take the expression of the expansion, okay, and then you think of multiplying and dividing the second order term by the square of h bar, okay, you find that the second derivative of E with respect to K divided by the square of h bar has the units of the inverse of a mass. Is a positive quantity. Of course it is positive because the second derivative is calculated in the minimum. So the second derivatives along the first, second, and third axis are all positive in the minimum, okay? Then we divide by the square of h bar, which is of course positive. We obtain a positive quantity whose units are those of the inverse of a mass. We call it 1 over MIA. Why do we have two indices? Well, index I is because the derivative is taken along the direction of Ki. So it is either the first axis or second or third. The second index, A, reminds you that we are calculating this in the minimum A. For instance, in silicon, we have 6 minima of the conduction band, so A goes from 1 to 6. Okay. This quantity is called effective mass, or the ith component of the effective mass of minimum A. So we have two simplifications. One is that we consider the symbol E sub EA as the difference between the total energy and the energy of the minimum, okay? And second is that we are introducing the effective mass, okay? So in this case, the second order, after these simplifications, the second order of expansion of the energy in the conduction band becomes this quadratic form, okay? So on one side, we are very happy because we have recovered a quadratic relation between energy and momentum. This is not exactly equal to the relation of a free particle for two reasons. Why is that? One is that the minimum is displaced with respect to the origin. In general, it is not in the gamma point, but this is no big deal, okay? The second difficulty is that in many cases, the effective mass is different when we calculate it on the first direction K1, the second direction K2, and the third direction K3. Okay. So these parameters are different. Okay. For this reason, we call the set of values of 1 over m as the inverse effective mass tensor. Okay. We must, in general, express it in tensor form. Okay. Why is this mass important? Because it can be demonstrated. We don't have time to do it, but it can be demonstrated that the inertia of the electron when the electron is subjected to external perturbations, weak ones, okay, is given by this mass, not by the mass of the free electron. And the reason is that we are inside a solid, okay? And you remember we have taken the average. So we are not really in free space. So the effective mass is the parameter that provides the information about how the particle reacts to external forces. So it gives you the inertia of the electron. And you can see that the mass is inversely proportional to the second derivative of the E of k relation. So the curvature, the second derivative, you remember, is the curvature, okay? And the inverse is the curvature radius, okay? So this gives you a more clear picture of what happens in the dynamics of the particle. When we calculate the density of state in energy, we follow exactly the same calculation as we already did using the notes, okay? So I'm not going to repeat this, okay? Because the calculation of the density of states is exactly the same, with only one difference, okay? That if you look at the final result, you remember the density of states is proportional to the square root of E sub E. Okay. And let's look at the first formula in the slide. Okay. So the density of states is this function. It is proportional to the square root of E sub EA. And constants, and these constants are the volume of the crystal, the square root of 2. Then we have pi squared. This, of course, corresponds to the three-dimensional case because it is the physically important one, okay? Then we have the cube of the of h bar, and then we have a mass to the 3/2, okay? So the only difference between this formula and the formula that we have analyzed 1 hour ago is in this mass. This mass is defined as the cubic root of m1 times m2 times m3, okay? So you see, these three masses may be different in a real semiconductor. Actually, like in silicon, they are different from each other, okay? But in the definition of the density of states, we have the product to the 1/3, okay? So this is called the average effective mass, okay? It is not finished yet because in a semiconductor, we may have more than one minima, more than one minimum, okay? In silicon, we have 6. So this expression provides you with the density of states of minimum of the individual minimum of index A, okay? Now we have to sum over the state, of the minima, sorry, because this product is the number of states around this minimum. In order to find the total number of states, we must sum over the minima. So the individual G sub A density of state is summed like this, with the index going from 1 to the total number of absolute minima of the conduction band. So We call it MC. MC is the total number of the conduction minima, of the absolute minima of the conduction band, okay? And it is silicon, in silicon it is 6, you remember. In gallium arsenide it is 4. Sorry, in gallium arsenide it is 1. There is only one minimum in the gamma point. And in germanium it is 4, okay? So when we perform this sum, actually, the only thing that is different depending on the index may be this mass, okay? All the other parts are constants, and this index A over the energy can be dropped because just energy is a variable, okay? So the index in the energy has no meaning now. So we must sum up over the mass from 1 to MC, okay? So we use a compact expression. We define some ME, the effective mass of the electrons of the conduction band. It is defined like this, okay? And the conclusion is that the density of states is given by this expression, in which we have the square root of energy, we have the effective mass of the electrons to the 3/2, okay? And we have the total number of minima, of absolute minima of the conduction band, okay? It is very easy to go from this expression to the expression of a combined density of states. Combined means considering also the density in the physical space. Why? Because we simply divide by the volume, omega, okay? So we introduce another symbol, gamma. Gamma is the combined density of states in energy and physical space. It is simply G over the volume. So it is given by this expression. It's constants times the square root of energy, okay? The density of state is very useful because since we have the parabolic band approximation, it is always a square root, and then we can use it in several calculations that are encountered in the theory. Now we must repeat the analysis for the valence band. You remember that in the valence band, in all semiconductors of interest, we have only 2 branches, okay? And these 2 branches are centered in the origin, okay? So in this case, the index A goes from 1 to 2 for the valence band of the semiconductors of interest. There is a difference, however, that when we apply the parabolic band approximation to the valence band, we have to expand, to Taylor expand to the second order, a function in the maximum. So the second derivatives are negative, okay? And this is obvious because in this case, E sub A is the maximum. So when we move away from the maximum, we go down, okay? So the second order term of the expansion is negative because the second derivatives are negative in the maximum, okay? Obviously, we don't like too much having negative masses, okay? So in this case, the effective mass, the inverse effective mass, is defined with a minus, okay? So for the valence band, 1 over m is minus 1 over h bar times the second derivative, so it turns out to be positive, okay? All the other part of the analysis is identical. We define, be careful, we define a quantity that we call E sub HA as the maximum E sub A minus the branch. So this difference is never negative, okay? Why do you introduce the symbol H? Because this stands for whole, okay? So this is the expression for the, it is the kinetic energy. We shall see it in a minute, okay? For the kinetic energy of the hole near the maximum of the valence band, okay? And again, it is quadratic. And again, the density of states is proportional to the square root of E sub H, okay? In this case, the coefficients contain a symbol MV. MV is the number of absolute maxima of the valence band, and it is equal to 2 for silicon, germanium, and gallium arsenide. MH is the average effective mass of the holes, okay? So from now on, we are going to use the parabolic band approximation, okay? In the next slides, I'm going to show you some parameters. Some of them are already known to you, okay? So we keep considering silicon, germanium, and gallium arsenide. You remember they have the face-centered cubic type of crystal, and the reciprocal lattices have the cubic body-centered structure, okay? When we indicate the value of the lattice constant, okay, we must specify the temperature because it's intuitive. If you increase the temperature, you expect that the crystal may expand, okay? So the lattice temperature will become larger, okay? So the lattice constant at 300 Kelvin for silicon is 5.43 angstrom, for germanium 5.66, and for gallium arsenide is 5.65. Okay. We have already discussed the form of the bands because we have used the figure. I just remind you that in the valence band we have two branches. The branch that is with larger curvature radius has a larger mass, and for this reason the hole belonging to that branch are called heavy. Those belonging to the other branch are called light. Now let's consider first the valence band, okay? The valence band for each of the two branches of the valence band, it comes out that the effective masses are equal to each other. So for the valence band, each branch of the valence band, the second derivatives of the branch with respect to K are equal to each other. That means that the branch is isotropic. The properties are the same in all directions of the K space. Okay. When we want to describe or indicate the values of these masses, instead of indicating the absolute values, of the masses. It is more convenient to express the ratio, you can see it in the table, between the mass of the particle and the mass of the free electron. Okay, so here m0 is the mass of the free electron. MHL is the mass of the hole that belongs to the light branch. Okay, so in the indices, the first H stands for hole and the L stands for light. And you see in the table that the masses are smaller than the free electron mass m0. They are, for germanium, 0.04, for silicon, 0.16, and for gallium arsenide, 0.12. On the right column, you can see instead the masses of the heavy branch. So MHH means the first H stands for hole and the second for heavy. Okay. You see that the effective masses depend on temperature. Why? Well, for the same reason as the lattice constant depends on temperature. If you increase the temperature of the lattice will expand. So the lattice constant will expand. The characteristic vectors of the direct lattice will expand. That means that the characteristic vectors B1, B2, B3 of the reciprocal lattice will contract. Okay. So the E of K relation that is defined in the first Brillouin zone will be deformed by this contraction. And so the curvature will change, and the curvature is the inverse of the mass. So the effective masses depend on temperature. However, this dependence is very, very small. So in the majority of cases, it can be neglected without any problem. The conduction band of the three semiconductors is different, as you remember, okay? In gallium arsenide, there is only one absolute minimum at the gamma point with spherical symmetry. So again, in gallium arsenide, also in the conduction band, the values of the effective masses along the first, second, and third direction are equal to each other. If you consider silicon, you remember there are 6 absolute minima of the conduction band. They are grouped into 3 pairs, and each pair is placed along one of the 3 directions, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so they are placed symmetrically around the gamma point. Okay, for instance, if you take the 1, 0, 0 direction, the 2 minima of the conduction band of silicon are placed at a position Km00 or minus Km00. So one of them is to the right of the gamma point and the other one is to the left of the gamma point. Km is 0.85 times Kb, where Kb is the distance between the gamma point and the X point. So it is the extension of the first Brillouin zone on one side of the origin. Okay, so the minima are relatively near the X point, but they are inside the Brillouin zone. For the direction 0, 1, 0, it is the same, but Km is in the second coordinate, And for the 0, 0, 1 direction, it is in the third coordinate. Now, still considering silicon, you remember the inverse effective masses are the second derivative of the E of K relation. So are these second derivatives equal to each other in silicon or different? They are different. Actually, out of the three derivatives, two of them are equal to each other, and one is different. And the one that is different is the one that is associated to the axis. So this is easily understood if you consider the equations. Okay, so look at the 1, 0, 0 case, okay, and consider the minimum that is on the right, so in the positive direction of the K1 axis, okay, with respect to the gamma point. You remember that the value of the minimum was called with the general symbol E sub A, but now we know that we are in the conduction band of silicon. All minima are equal to EC. So in the formula, we are using EC, okay? So if we number this minimum with 1, we have that the kinetic energy E sub E1 is the branch minus the minimum EC. It happens to be given by that equation, h bar squared over 2. And then we have an expression that is quadratic in K, in which along the first direction we have K1 minus Km, because you remember the minimum is placed at Km 0, 0. And this is divided by ML. ML is a value of the effective mass that is the inverse of the second derivative with respect to K1. ML is called the longitudinal mass because it is associated with the axis K1. The other two terms have K2 squared over some MT. MT is called transversal mass. And the third direction again has K3 squared over MT again. Okay, so we have two transversal masses and one longitudinal mass. So two coefficients are equal, one is different. Geometrically, if you fix the value of the kinetic energy E sub E1, geometrically in the K-space, this is an ellipsoid of revolution about the 1, 0, 0 axis. Okay. When you move to the second equation and you consider the axis 0, 1, 0, then the longitudinal mass is associated to K2. And the transversal masses are associated to K1 and K3. And finally, when you consider the 0, 0, 1 direction, then the longitudinal mass is associated to K3, and the transversal masses are associated to K1 and K2. This is related to the three minima that are in the positive, on the positive sides of the origin with respect to the first, second, and third axis. Those that are on the negative sides, the remaining three minima, are simply found from the above expression by replacing Km with a minus Km. Okay? Next, we go to germanium. Germanium is like silicon, meaning that along each 1, 1, 1 direction, two of the masses are equal, we still call them transverse or transversal, and one is different, it's called longitudinal, and the position of Km is equal to the boundary of the Brillouin zone. Okay. It is interesting to note that if we consider these expressions, this is for gallium arsenide, okay? And you fix the energy, this is the equation of a sphere, okay? Because the three coefficients are equal, okay? And in gallium arsenide, and the sphere is placed in the origin because Kia is 0 because we are in the gamma point, okay? So a surface of equal energy in gallium arsenide, in the conduction band of gallium arsenide, is a sphere. Instead, if you consider silicon or germanium, the surfaces of equal energies near the minima of the conduction band are ellipsoids of revolution. So I think I have a picture of them. I'm going to look for it. Okay, so let me change the screen. Here we are. So if you look at the right part of the figure, for gallium arsenide, near the minimum of the conduction band, we have a surface of equal energy. So this is the K space, and the sphere that you see is the surface of equal energy. So we fix the energy near the minimum, okay? And it is a sphere because of the spherical symmetry of the minimum. By the way, also the two branches of the valence band in these semiconductors have a spherical symmetry. When you consider silicon, you have 6 minima symmetrically placed with respect to the origin in the 3 direction of the K vector, 0, 0, 1, 1, 0, 0, 0, 1, 0. And the surfaces of equal energy are ellipsoids of revolution. So those forms that you can see in the figure are ellipsoids. The same applies to germanium. You have 8 minima, but you must consider only half of them, so it's 4. And they are placed along the 1, 1, 1 direction. You see the symbol here. This is 1, 1, 1 with the minus sign on top, as they do in crystallography, okay? These are minus signs on top of the ones. And also in this case, we have two transversal masses and one longitudinal mass, so we have ellipsoids of rotation. Let's have a look at the numbers. In this table, you can see the values of the longitudinal and transversal mass for germanium and silicon. And also gallium arsenide, but gallium arsenide has a spherical symmetry, so the longitudinal and transversal mass are just the same, okay? You can observe immediately that the mass of gallium arsenide is much smaller than the others, okay? And this has an impact on the performance of a device. You remember the mass describes the inertia of the particle when we apply an external field, okay? So essentially, if the mass of the particles is smaller, we expect that they will react faster, okay? And so the material will behave better to the application of an electric field. We may get more current, or the switching of the device will be faster if the mass is smaller, okay? So we expect that gallium arsenide has better performances in terms of current and velocity. I mean, devices made of gallium arsenide should be better than those made of germanium and silicon, okay? This is true. This is true. So high-speed devices sometimes are manufactured or used to be manufactured using gallium arsenide, okay? On the other hand, there is a difficulty that gallium arsenide is a compound semiconductor. And the technology of compound semiconductors is much, much more difficult than that of pure materials like silicon and germanium, okay? So the enhancement in speed and performance can be obtained, for instance, with silicon, simply by scaling, by making the devices smaller and smaller and smaller. And this is much, much easier with silicon than with gallium arsenide, okay? So actually, gallium arsenide is not used that much, okay? Another observation is that for both germanium and silicon, the longitudinal mass is significantly larger than the transversal mass, okay? For silicon, it is about 5 times larger. And for germanium, it is even larger, okay? So that means that in the material, we have a mixture of heavy electrons and light electrons, okay? And the properties will also be averaged, okay? So the velocity, the ability to react to fields will be averaged because there are also heavy electrons that react not so well to the field, okay? So it would be preferable to have in silicon, for instance, only light electrons, okay? This is somehow possible in the technology because this is not obvious, but if the material is subjected to a mechanical tension, the position of the valleys will change, and you may manage to displace the valleys in a way that the longitudinal valleys are not populated. Okay, so you make the longitudinal electrons, so to speak, to disappear, or the electrons having a longitudinal mass aligned with the field disappears. It is not obvious, okay? You need to go deeper into the physics to see that, but there is a way of obtaining that the population of electrons that react with the transverse mass to the field is dominant. Okay. The other comments that are here in the slides, I think, were already made while discussing the figure. Okay. So about the curvature, about the secondary minimum of the conduction band of gallium arsenide, and the possibility of building lasers with gallium arsenide. So since this completes a block of material, I would like to stop here and not start another block now. So we stop for the moment. We still have a few minutes if there are questions. Otherwise, we shall meet again on Thursday. If there are questions, please open the mic and ask them. Okay, so no questions, so I thank you, and we meet again on Thursday afternoon. Bye-bye.